Hello dear audience, thank you so much for being with me in another tutorial video of a deep learning course. We said that a nonlinear function can be added and perform the calculations on the new set of features. We can repeat this several times. With this repetition, we have more layers and a more complex function. These more complex functions can solve more difficult problems. That's the difference. In this code, with 11 lines, a two-layer neural network is implemented. In Python, no other software was used. Of course, this is not my code, and I put the source here for you. Apart from NumPy, which is used to generate random numbers and matrix multiplication and vector multiplication, this code did not use any other libraries. These SYN, which you can see here, are the weight matrices, and X and Y are input and output. We said that we repeat the gradient descent algorithm as much as we have time. First, we calculate the first layer from the input of the weights. It means the differential with respect to the first layer, differential with respect to the second layer. Then, based on these differentials, we update the weights and then repeat this work again. So it is not difficult to implement. Let's explain the forward step to you. By multiplying X and W, we get H. Of course, we also apply nonlinear functions such as max. Then by multiplying H and W2, we get S. The forward step is very simple. In the backward step, we first calculate the D-score. Here, this D-score means the division of D-loss into D-score. Then we will calculate the division of D-score into the DH in the next step. It means we are going back layer by layer, and in the last step of this, we want to calculate the division of DH into W1 and multiplied in to the division of DL into W1 and multiply the result into the division of DL into W2. When we have the gradient, we can update the parameters so that our neural network works better. This was without neurons perspective. Now, if we want to add neuron discussion, we can do it. But this is not an approach that can be used now. That is now. The famous saying is that neural networks are not neural networks at all. They have nothing to do with neural networks at all. That's why you rarely see in a book, don't say this, the brain is this, now we are inspired by the neural networks in the brain. This is not really happening. But if someone wants to know why they are called artificial neural networks and how they are related to biological neural networks, let me give a very brief explanation. The brain is made up of very simple computing units. Now I say very simple. Each of them is a complete computer. They receive an input and have an output. This input can come from other neurons in the brain. We have 100 billion neurons. A simple calculation is performed by this entry, similar to the internal multiplication that we do. It seems to calculate the similarities, and finally it delivers an output that this output goes to another series of neurons through axons. This alone, it is true that the calculations are complete, but it is very simple. There is an aggregation process that we do here in artificial neural network. Here the x's are the inputs and the w's are the weights. x0 is multiplied by w0, x1 is multiplied by w1. That is an internal multiplication. The same thing that we do in natural neural networks. We do a sum and then the calculated set, this potential is created. If the ratio of the potential difference inside the membrane to outside the membrane exceeds a certain limit, something similar to function is applied on it. Now the power of the brain is in these numbers. The discussion raised in neural networks at the beginning was that if we increase the number of these networks, then we can reach the power of the brain or artificial intelligence. Of course, this view was not correct. And for a long time, no university or a center for neural networks was considered a fund until finally the discussion of deep learning was raised. Our preference is the same layer view because it is better in both understanding and implementation. The reason why I said that artificial neural networks are actually not neural networks at all is because the modeling we have done was accompanied by a lot of simplification, so that artificial neural networks can no longer be considered a simple model. You knew about biological neural networks. There is always some abstraction in modeling, but here this simplification is too much to the extent that it is not possible to find a connection between the two. They thought like this 20 years ago. But now the layered view is preferable. Well, we said that we definitely need an activity function to increase productivity. Historically, it has been very subordinate to the famous sigmoid. This function is S-shaped. Sigmoid means like S. But this function is between 0 and 1. That is, at negative infinity, it returns 0, and at positive infinity, it returns 1. And between these, it returns values between 0 and 1. This function has been used the most in the history of neural networks, but now it is no longer used. One reason is that there is exponentiation inside. You know that the act of exponentiation is an expensive act. When there is a lot of repetition, this time-consuming becomes more important. The second reason is that the output of this function is numbers between 0 and 1, and as a result, their average is not 0. This problem becomes problematic. You can read the problems in the slides, but in short, it slows down learning, and the straight path becomes a zigzag path. To solve this problem, the hyperbolic tangent function was introduced, which is similar to the sigmoid function, but the outputs are between -1 and +1. Now the average becomes 0, but the exponentiation problem still exists. Similarly, there is also the issue of saturation. That is where the slope of the function is very low, no learning happens. From the gradient, we understand how much we have to move. where the slope of the function is very low, the gradient is almost zero. So no learning will happen. In recent years, the suggestion is to use max or ReLU function. Very simply, if x is greater than 0, we return x itself, and if x is less than 0, it returns 0. This is a linear binomial function. In 2013, Mr. Gerdaffellow said that instead of 2 pieces, we should make 3 pieces and 4 pieces. They called it max out. Currently, ReLU is used by default in deep learning. Suppose we want to solve the same Seyfarth problem. One thing we have to choose is the neural network architecture. I have used the same old Neuronian point of view here. We have an input layer, which is a series of numbers. We turn these into a new vector of features, and now we calculate the scores based on these. How should the network equation be? The inferences which are known have dimensions of 3 multiplied in 32 multiplied in 32. The outputs are also known. We have 10 classes in Seyfarth problem, so we have to calculate 10 scores. How should the hidden layers be? 1 layer, double layer, 3 layers. In practice, more than 2 layers are not used, because with a 2-layer neural network, and function can be estimated with any accuracy, and there is no need for more layers. This architecture is called neural network. When the number of layers increases, the number of parameters also increases. A lot of data is needed here. In the past, this much data was not available because there was no such thing as Google. In the past, data limitations, GPU and technical limitations prevented us from increasing the number of layers to more than 2. Now, theoretically, we can have any number of layers. Now Google has deep networks with 1,000 layers. Google has both enough data and enough computing resources. Therefore, it can increase the number of layers as much as it wants. These layers are called completely connected layers. I said that one of the differences between deep learning and normal neural networks is that both the number of layers is greater and the variety of layers is greater. For now, we don't have one more layer type here, fully connected layers. What does it mean? That is, each neuron in the previous layer is connected to all the neurons in the next layer. Here we are implementing a single neuron. Neuron receives its input, it multiplies the weights, the similarity is calculated, it is added with bias, and now a nonlinear function is applied. This view is no longer a suitable view. A better view is the view of the layer. The purpose of TensorFlow and PyTorch and these facilities that are available now is to simplify these implementations. Now we want to implement a 2-layer neural network. We define the function f as the activity function. We generate a random matrix. Based on these raw calculations, we generate a series of new features. How? We multiply these x's by a w and add them with a b. This becomes a linear transformation, and then we apply the nonlinear function, usually from the ReLU family, on them. In fact, we generate a series of higher level features from the basic raw features. We can repeat this again. That is, we should not calculate the score directly from these, but let's change these features ourselves to a series of higher level features which are more useful for classification. For example, in the first step, let's distinguish the lines from the pixels. Identify the geometric shapes from the lines and then make the classification more easily and accurately from the geometric shapes. Thank you so much for being with me in another deep learning tutorial video. I will explain more detailed and noticeable concepts in the upcoming lectures. So stay tuned. Have a nice day.